In this chapter, we're going to look at something different and start talking about probabilities and counting. So in the first two chapters, you learned about descriptive statistics, right? So taking that sample data and finding the mean, the median, maybe the mode, the standard deviation, the variance, looking at the graphs, really analyzing the shape of the graph, and really just kind of analyzing that data. The second branch of statistics is inferential statistics, which is where we're going. And the foundation of inferential statistics is really about probabilities. So this chapter is going to be all about probabilities. The result of a single trial in a probability experiment is called an outcome. And the set of all possible outcomes of a probability experiment is the sample space. So your sample space is basically everything that could happen or anything that could happen. Okay. So all possible outcomes. And then an outcome refers to what actually does happen. So a particular specific outcome, not just in general. An event is a subset of the sample space, and it could consist of one or more outcomes. So we'll look at some examples. I think this will make a little bit more sense. So example one, a survey consists of asking people their blood types. So you could be blood type O, A, B, or AB. And it also includes whether you are Rh positive or Rh negative. So a lot of times people will say, oh, I'm A positive or I'm A negative. So that is part of your blood type as well. So we want to determine the number of outcomes and identify the sample space. And we're going to use a tree diagram to show the various potential outcomes here. So a tree diagram is really just a picture that involves branching. You can go in your book for an actual full definition, but I thought it'd be easier just to do it together. So let's go ahead and do that. So this is going to be my diagram. So you can do them kind of horizontal or vertical. It really doesn't matter. I'm going to do a vertical one here. But there are 4 types of blood types, right? So you could be 0, you could be A, you could be B, or you could be AB. Okay, so just kind of starting off here. So either you're O, I think I said 0. You're O, A, B, or AB. Sorry if I said 0. I'm so used to just thinking math. And then under that, you could either be positive or negative. So you could either be positive or you could be negative, right? You could be positive or you could be negative, meaning Rh positive or Rh negative. So what are your possible outcomes here? Well, you could either be O positive or O negative, A positive or A negative, B positive or B negative, or AB positive or AB negative. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 possible options here. So there are 8. Okay, possible outcomes. In our sample space, we would write like this. Usually we use little like, I'm gonna write down here, little like brackets there, braces. So we would write it as O positive, O negative, A positive, A negative, B positive, B negative, AB positive, or AB negative. So your sample space includes all possibilities. So it's anything that could happen, all possible outcomes. Obviously, every person is not every one of these, right? You would be one specific blood type, but these are the 8 possible blood types, the 8 possible outcomes that you could have there. So this is your tree diagram, just a branching diagram. Now, in the rest of this chapter, you will learn how to calculate the probability of a likelihood of an event. And often to do that, we need to know the sample space first. So you need to know how many possible outcomes there are in order to find probabilities. Events are often represented using uppercase letters. So you're going to see uppercase letters used a lot for events that consist of a single outcome. Is called a simple event. So an event that consists of a single outcome, we use the word a simple event. For instance, consider the probability experiment that considers tossing a coin and then rolling a six-sided die. Let's use a tree diagram to visually show all possible outcomes. So there's two things happening here. We're going to toss a coin and we're going to roll a six-sided die. That's a standard die. So if you toss a coin, you could either get heads or tails. And if you roll a die, you could get the numbers 1, 2, 3, 4, 5, 6. Now I know they look like dots, right? It's like 1, 2, 3, and so on. But we can just use the numbers to represent the sides here. So let's see what could happen. Well, first thing is you could have heads or you could have tails, right? And then if you have heads, you could get the number 1, you could get the number 2, the number 3, the number 4, the number 5, or the number 6. I'm just kind of doing a little mini tree diagram here. Or for tails, you could also get the number 1, 2, 3, 4, 5, and 6. So what are options that you could get? Well, you could get heads number 1, heads number 2, heads number 3, heads number 4, heads number 5, heads number 6. You could get tails 1, tails 2, tails in number 3, tails in number 4, tails in number 5, or tails in number 6. So there's 12 possible outcomes here. So just to kind of have it, our sample space is that H1, H2, H3, H4, H5, H6, and then T1, T2, T3, T4, T5, T6. So we have 12 possibilities here for our sample space. Okay. So this shows us all possible outcomes, right? So we have 12 possible outcomes for our sample space. So there's 12 different things that could happen. Now, the event tossing heads and rolling a 3 is a simple event and can be represented like this, right? So if we call this event A, then H3 represents the idea of tossing a coin and getting a heads, and then rolling a die and getting a 3. So both of those things happen, right? Let's say at the same time. This is a simple event because it consists of just one outcome. So there's only one option, one thing that can happen there. Let's look at a different event. Let's say your event is tossing a head and rolling an even number. Well, tossing a head and rolling an even number could be H2, H4, or H6. There's 3 possibilities there. So because there are 3 possibilities, this is not simple because there are 3 possible outcomes. Okay, so if something is a simple event, it only has one outcome. If something is not simple, it can have more than one outcome. So this is a simple event. There's only one thing to get that to happen. Whereas here, event B has 3 different options to have success there, right? So simple event, one outcome, not a simple event, more than one outcome. Example 2. Determine the number of outcomes in each event and then decide whether the event is simple, sorry, let's just say or not. So for 1, for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So I just circled it here. Notice here that event A is selecting a specific defective machine part. So there's only one outcome here, right? You're selecting a specific defective machine part. So there's one outcome, right? Selecting that specific part. So this is a simple event. For the next example, you roll again a 6-sided die, so your standard die, and the event is rolling at least a 4. Well, think about this. If we're rolling at least a 4, you could get a 4, a 5, or a 6. All 3 of those would satisfy event B. So because you have 3 outcomes, this is not simple. Okay, so one outcome, simple. More than one outcome, not simple. Now, in some cases, an event can occur so many different ways that it may not be practical to write out all outcomes or to make a tree diagram. It could just be too much. So we have what's called the fundamental counting principle that can be used to find the number of ways two or more events can occur in sequence. So in sequence meaning like in order. The fundamental counting principle says that if one event can occur in m ways and the second event can occur in n ways, then the number of ways the two events can occur in sequence is m times n. This rule can be extended to any number of events occurring in sequence. So if we know how many ways each individual event can occur, then we can combine them together by multiplying to figure out all the possible ways. So for instance, let's say you're purchasing a new car and the possible manufacturers, car sizes, and colors are listed in the table. So these are the options that you're thinking of. You're considering a Ford, a GM, a Honda. You want a compact or a mid-sized car, and you're interested in white, red, black, and green for colors. How many different ways can you select one manufacturer, one car size, and one color? And we can use a tree diagram to check our results here. Well, let's use the fundamental counting principle first. So if I think about manufacturing, there are three choices. If I think about the size, I have two choices. And if I think about my colors, I have four choices. So what the fundamental counting principle tells us is there would be 3 times 2 times 4. So that would be 6 times 4 is 24 different combinations. So, and we can check this with a tree diagram. So let's kind of do a quick one here. I don't know if we'll do the full thing out, but let's try it. So first thing you're going to choose, let's say theoretically we're going to go in order here, is your car. So you could either pick a Ford, right, a GM, or a Honda. And then from there, you can either pick, I'm just going to use C and M here, a compact car or a mid-sized car. And then you can choose the color. So under the Ford for the compact cars, you could get white, red, black, or green. And the same thing is true under the midsize, white, red, black, or green. And I'm going to run out here. Same thing on these guys, right? This one also gets white, red, black, and green, white, red, black, and green, white, red, black, and green, white, red, black, and green. So what's going to happen is you're going to end up with 4, 8. Here is going to give us 4 more, so 12. And then another 4 is 16. And then another 4 is 20. And another 4 is going to be 24 combinations altogether. So for instance, one combination is a Ford car, a compact, and make it black. Or a Ford car, a compact, and make it white. Those are all different combinations. And you can see in your text, I'll just show it to you quickly. They have a nice tree diagram here with all those possibilities, right? So there are 3 cars, compact and midsize, and each one has the option of 4 colors. So if you look at the final row, you do have 24 different combinations here. But that can be very cumbersome to write out every single time. So now we have a faster way to find out how many combinations we could make. Okay. The access code for a car security system consists of 4 digits. Each digit can be any number, 0 through 9. How many access codes are possible when each of the following occur, right? So you have, let's say, box 1, 2, 3, 4. So you have 4 different numbers for your access code. So some cars actually have codes where you don't need a key, right? You can enter the car using an access code. So this one has a 4-digit access code. Let's look at the combination. So in the first case, each digit can be used once and not repeated. So let's think about this. In the first case, you could use numbers 0 through 9, right? So you have 10 options there that you can use. Well, we can't repeat. So let's say I use 9 in the first one. I can't use 9 in the second number here. So I don't have 10 options anymore. I only have 9 options. And let's say I use the numbers 9 and then 1. So maybe I use 9 and then I use 1. Well, now I can't use these 2 numbers anymore. So for my third choice, I only can choose from 8 options, right? 0, 2, 3, 4, 5, 6, 7. and 8. So I have 8 options there. Maybe I choose number 5. And then the last case, again, I can't repeat it, so I can't repeat any digits. So now I'm down to 7 options here. So how many combinations could I possibly make? Well, if I multiply this all out, there are 5,040 different combinations that you can make here with those numbers. Let's try another one. Here, each digit can be repeated. So if each digit can be repeated and you have 10 choices per digit, right, because we're including 0, then each box has 10 choices, right? You can choose 9999 if I wanted to. So I have 10 choices for each box. So I have 10 choices for the first box, 10 for the second, 10 for the third, and 10 for the fourth. So I actually have 10,000 possible combinations here. And then finally, let's assume that each digit can be repeated. So this should say but the first digit cannot be 0 or 1. So if I can't use 0 or 1 for the first digit, that only leaves me options 2, 3, 4, 5, 6, 7, 8, 9. So I only have 8 options for the first one. But for the other ones, I can repeat and there's no restrictions. So I would have 10 digit choices for the other 3. So I have 8,000 different combinations. Okay, so you can see that we wouldn't be able to really write out a tree diagram for this. I mean, I guess we could theoretically, but it would take so long. So here, that fundamental counting principle is really helpful. And now you can see why your passwords are so important, right? So the longer your passwords are, the more symbols and combinations of numbers and characters you use, the more combinations you're getting. So if you have a password that's 10 characters long, and you're allowing the 26 letters of the alphabet, you're allowing capital and lowercase, so now you have 52 options, you're allowing digits there, you're allowing symbols, you're just really expanding on how many possible combinations you could have, which makes it harder to find your combination.